So our next unit goes along with chapter 17 in the book, and it's really all about this question: what drives a reaction to be spontaneous? And so, you might be asking, like, what do we mean by spontaneous? And this picture kind of helps. We can start out with a really nice, clean room, and it seems like without much of anything happening, it all of a sudden turns into this, kind of mess of a room. And it's certainly going to take more energy to get it back to being all clean, but it just spontaneously happens on its own. And so that's really what we're talking about here. But of course, with reactions instead. So there are two things that are going to be involved with this, and one is enthalpy. That's that delta H that we talked about before. So remember, that's the heat content. Exothermic reactions are generally favored, and so that would mean that we would have a negative delta H if it was exo. And the other factor then that is involved is entropy, and so this is the new part. This is symbolized with a delta S, and this is really describing the disorder of a system. And so if we have an increase or more disorder, that's favored. So, if we think about this increased disorder of the bedroom is actually favored, as opposed to everything being perfectly in their spot. Nature tends towards chaos. Think again about that room at the end of the week. Your mom would love this law, or maybe they wouldn't love this law. You might love this law, and just being able to say, well, my room just tends towards disorder. But spontaneous reactions then are those that occur without outside intervention. Yes, we may need to add some activation energy to get them started, but once they're started, they will continue on their own. That can occur either fast or slow. Remember, that's what we studied with kinetics. It can, some are super fast, like combustion of hydrogen. Others are really slow, like graphite actually turning into diamond, but they will all continue on their own once they have been started. So entropy is where we want to start. And entropy relates to really the second law of thermodynamics. So the second law of thermodynamics says that the universe is constantly increasing in disorder. And so Rudolf Clausius, which, we'll maybe talk about him a little bit more later on, actually, we're probably not going to worry about his equation for vapor pressures, but he actually discovered this, or basically theorized this. And, again, we want to always think about entropy in terms of the amount of disorder. The third law of thermodynamics then also relates to entropy, and that says that entropy of a perfect crystal at 0 Kelvin is 0. Well, there aren't a lot of perfect crystals out there, okay? Entropy values are rarely ever 0, even for elements. So the big thing here is this means that the absolute entropy can be determined at any temperature higher than 0 Kelvin, okay? So that can be handy to keep in mind. We'll talk about G later in this unit, but that delta H was 0 for an element, but it's not going to be 0. You should not expect S to be 0 ever. So if we're talking about entropy, yes, can be described as the amount of disorder, but it can also really be described as kind of the number of possible arrangements of our particles. And so you can kind of see that here with this picture, that, if we start out, we have arrangement 1, arrangement 2, arrangement 3. How many variations of that can there be with even just, 4 particles here? So, arrangement 1, we can only have that in one kind of what we call a microstate, or kind of organization. Depending on, if we kind of tagged each of these and numbered them 1, 2, 3, 4, we could have 4 different ways of doing state 2. We could have 6 different ways of doing state 3. And that increasing number of what we call microstates is actually basically increasing entropy. So this would have the most entropy because we have the most ways of organizing those 4 particles there. So our big rule here is really that we're looking for greater disorder, okay, or greater randomness in our system, and that's going to mean that there's a larger entropy. Now, how do we actually tell if there's a larger entropy or not if we can't exactly count out all of these little microstates like this with, small numbers of particles? Well, we can look at a couple of different things. First of all, and this is probably the biggest one, that entropy will increase for a substance as it changes from a solid to a liquid to a gas. So our gas is going to have the most entropy and our solid would have the least. Okay, solids have the most order, okay, or the least disorder. Gases have the most disorder, okay. We also can see here when we have a pure solid or a liquid and it dissolves. So if I get something to dissolve, it's going to increase the entropy. There are some exceptions. Carbonates are actually an exception. But generally, as we dissolve something, it's going to become more disordered. Okay? We can also think about basically when a gas escapes from a solvent. Okay, so it's been trapped and now it's escaping. It's becoming more disordered as it escapes from that. And then we also have entropy increasing with increased molecular complexity. So increasing molecular complexity, meaning like we have more atoms in our formula. We could have more carbons in a chain. We could have bigger molecules. When we have something like DNA, there's many, many more of those microstates here that could occur, making for greater disorder or greater possible number of microstates. And then finally, we can also look at reactions. Increasing the number of moles of particles are oftentimes going to increase entropy. And so in general, we can look for that, but all of these factors, we sometimes have to look at multiple things happening at once. So we'll look at some other ways to more quantitatively determine this. In general, though, the greater the number of arrangements, the higher the entropy in the system. So again, the more microstates that we could have, the more entropy, the more disorder in that system. So we can do some predictions then with a couple of things here, predicting the sign. Again, if we have an increase in disorder, it's positive for delta S. If we have a decrease in disorder, it is negative for delta S. So take a second and try exercise 2 and see what you think. Okay, so if we start out with a solid and it is added to water to form a solution, it is actually dissolving, so we should expect that this is an increase in disorder, so it should be a positive delta S. Iodine vapor condenses, so here we have a gas going to a liquid. Oh, actually, not a liquid, it's forming crystals, so that's actually going to be forming a solid. So that's actually going to be a decrease in disorder, so a negative delta S, a decrease in entropy. So like I said, we can actually calculate entropies. Let's save that for a second and just think about kind of conceptually, which do we think is going to have the largest increase in entropy here? And pause the video and try that. Take a look and see what you think. So it's not often that we're actually asked to do something like this, necessarily predict it with kind of so little information potentially. But if you are asked that, you kind of want to think of a hierarchy here of what's going to cause the greatest increase in entropy. And the first thing to think about is, do we have a gas compared to a liquid compared to a solid? Okay, that's going to be probably the most important factor. 2, we can think about the molecular size. 3, we can think about the number of molecules. 4, we can think about, is it dissolved or not? And then 5, we can think about, is temperature playing a role there? So if I look at this one, really probably the one that's going to have the biggest change or increase in entropy is going to be A, because we have our solid going to a gas. That's probably going to be the one that has that largest increase. So like I said, it's pretty hard to predict a lot of times, but we can definitely calculate it. And so we have this equation here for delta S, and this is delta S for our reaction. Notice it's being called Big Mama verse 2 because the first time we had a Big Mama equation, it was really for delta H. It was the same format here, but we had H in there. So now we're going to be looking at entropy of products minus entropy of reactants. So this should be bringing back some memories. When we have delta S then as a positive, that means the disorder is increasing and that is favored, meaning that it's going to be likely that the reaction will occur. And then when delta S is a negative, disorder decreases. Notice here, and we have to be careful later on with this especially, but units for S are in joules per Kelvin per mole. Okay, again, that thinking about how those are in the denominator, those are both Kelvin and mole in the denominator down there, so be careful. They are not in kilojoules, and that's going to become a little tricky later on. But we're going to use a table of values just like we did before. So in this case, we're going to actually look at Appendix 4 again. So you should look for that posted in Schoology. So let's go ahead and try this one and see what we get. Again, we're going to take our product here first. And so in this case, it is the SO3 here. We have 2 moles of that, so we do have to account for that. So our delta S for the reaction will be 2 times 256.6, and again that's joules per Kelvin times mole. Remember, this 2 here is really 2 moles because we've gotten it from the equation, and so our moles will end up canceling out, and we'll just have joules per Kelvin. We're going to subtract from that our values for the reactants, so we'll have 2 times SO2 will be 248.1, and I'm going to add to that my amount for O2. It has a coefficient of 1, so I don't need to multiply by anything, so plus 205.3. If I go ahead and do some math, you will see that we have a delta S then of negative 189.3, and that is joules per Kelvin. So is this an increase in disorder? No, it's actually a decrease in disorder. And if we think about it, we went from 3 moles of gas down to just 2 moles of gas, so that maybe makes sense that we would predict that we would have a decrease in entropy as we decrease the numbers of moles of gas. One thing I do want to point out, it does say on your handout that you have the answer there, but it is off by 1, so it should be a negative 189.3 instead of 188. Okay, one of the other ways that we can calculate entropy is if we are thinking about it occurring when a phase change happens. And remember that phase changes are going to occur at a constant temperature, so if we think about kind of that graph, of the heat being added versus time, our phase change would have been in these flat spots here. So that's kind of what we're talking about here, and really delta S then can be calculated by taking that heat transferred divided by the temperature at which it occurs. It's important to realize, again, our temperature here has to be in Kelvin, and because we wouldn't want to divide by 0 at any point, that's not going to work. And it's also important to note if the reaction is endothermic or exothermic, okay? The sign is going to matter. So, the actual significance of this is really dependent on the temperature at which the process occurs. Again, kind of think about it this way. If you gave a millionaire $100, it would not make much difference in his happiness, but if you gave a poor college student $100, it could create a totally different expression of happiness. And so that's really going to make a world of difference here. So the equation really that we're looking at, and this is going to come into play more later on, but is that delta S equals negative delta H divided by T. Notice that the negative is there, so we have to keep track of that. We'll plug in our delta H with its own positive or negative value into that. Again, give signs to those delta H's based on if they're endo or exo. Again, exo is going to be negative. Okay, so let me just remind you, exo is a negative delta H, whereas endo equals a positive delta H. Okay, that's going to be important. So if we take a look at an example here, we can think about these two reactions, and we want to calculate delta S here for each of these reactions. Notice it says it's at 25 degrees Celsius and 1 atm. So we have some delta H values given, and we just need to calculate. So go ahead and give this one a shot, and then we'll check. Okay, so you should have gotten 419 joules per Kelvin, or 0.419 kilojoules per Kelvin, either one. But this one is a positive, so we do have an increase in entropy for that very first reaction. The second reaction, you should have noticed that you got a negative value for that, and it's pretty negative. It's to the 10 to the third power for joules per Kelvin, and so we have a decrease in entropy for that. So that second reaction certainly is not as favorable, which we also can get an idea of from the delta H value being positive. Endothermic reactions typically are not as favorable. Okay, so to summarize, remember delta S is, if it's positive, it means it's more disorder, and that is favored. Negative delta S means more order, which I should really say less disorder. I really like thinking about it in terms of the amount of disorder. Okay, so less disorder. And whether a reaction will occur spontaneously may be determined by looking at the delta S, okay, which this is the delta S of the universe, okay, meaning our system and our surroundings together. And so our universe is overall looking for increasing entropy, increasing disorder. And so if the reaction is increasing it, it should be spontaneous. If it is not increasing it, it will be a non-spontaneous reaction. So generally we can determine it from that, but that's not always the case. So let's just take a look at an example here. So let's say we were looking at this reaction where we have hydrogen and oxygen reacting to form water. Like if we ignite them, the reaction is really fast, okay? Our entropy, actually, because we're going from 3 moles of gas down to 2 here, is a negative 88.9 joules per Kelvin. And so the entropy is decreasing. But we can also then go ahead and calculate our entropy of the surroundings using our delta H. And if we go through that calculation, we use our delta H, basically our system and our surroundings here. Our delta H ends up switching to a positive when we're talking about our surroundings. And overall we get a positive 1620 joules per Kelvin. And so, you know, we can go ahead and find that delta S for the universe, and we do see that when we take hydrogen and oxygen and burn them and they create water, they will actually create a positive 1530 joules per Kelvin for the universe. And so here's the thing that's important. Even though that entropy of the system declines, the entropy change for the surroundings ends up being so large that the overall change for the universe is positive. So this is, again, bottom line. A process is spontaneous in spite of a negative entropy change as long as it is extremely exothermic. So as long as something is basically giving off enough heat energy, even if the entropy is negative, it can be a spontaneous process. So we need to look at those two factors together, and that's what we're going to look at in our next set of notes. The very last thing that I want to point out are the equations that you'll see for this unit, actually for our last two units here, that are in the thermodynamics section. This is at the end of the equation packet. And so, we have used this delta H reaction or delta H equation before, but now we're also going to use the delta S and delta G equations. We will also be using these other equations here to go along with delta G. And then in our next unit, we will use everything else down here, but we will see one part of that come in just a little bit here, okay? So pay attention to those, pay attention to the different things that we have here as, definitions for things, but make sure that you're looking at that equation sheet.